Today we're going to talk about initial value problems. We last time introduced the antiderivative, but I didn't really give any indication of why this would be useful for anything. It's a weird thing to try and do the derivative backwards. It turns out it is useful for quite a bit of things, quite a lot of things. And one of those contexts is what we call initial value problems. It's based on a very simple fact, and that is the integral of a derivative of something. What's the integral of the derivative of something? This means, what is the function whose derivative is f prime of x? Well, the answer is f of x, right? This is the antiderivative of the derivative. You should feel like they cancel out. That's the whole point of this. The antiderivative is undoing the operation of the derivative. So what you get is the original function, again, f of x. What that means is, if we know f prime of x, we can find f of x by doing the antiderivative. Let's just do an example. This is an example of something generally called an initial value problem. Here it is. It says, I'm telling you that f prime of x is 2 to the 3x and f of 0 equals 10. You'll see why this is important. Find f of x. I gave you the derivative. Your job is to find the true value of the function. We're just going to use this basic fact. F of x is the antiderivative of the derivative. So f of x should be integral of f prime of x dx, right? And they told you what f prime of x is, so it's just going to be integral of 2 to the 3x dx. How do you do this integral? Well, you use the rules. We got rules for that. What do? We got rules for this. Remember the rule we talked about last time, integral a to the kx dx. This is the rule to use. It is a to the kx over k ln a plus c, right? So I'm going to use that rule here. The a is 2, the k is 3. I get 2 to the 3x over k is 3 ln of a, which is 2, plus c. All right? This is f of x. Okay, great. This is almost the whole answer to the whole problem, but this plus c, this pesky little plus c, I don't want to have an unknown constant in my answer. My answer should be like a specific function with no unknown constants in it. How do we find the plus c? We use now, in order to find c, we use the other random fact that was given to us at the beginning, which was f of 0 equals 10. That's why this is called an initial value problem. You can think of f of 0 as some kind of initial value for the function. Initial meaning first, like the value at 0. Use f of 0 equals 10. How can we do that? I'm going to take this formula that I just found. That's not my answer yet because I need to find the c. We are going to plug in x equals 0, because that's the 0 here, and then set equal to 10. So f of 0 equals this with a 0 plugged in, and it's 10. So I go 10 equals 2 to the 3 times 0 divided by 3 ln 2 plus c. And this now I can solve for c. It has no x remaining, so it can be solved for c. Can we simplify or anything? 2 to the power 3 times 0. This is 2 to the power 0, which is just 1 up top. So this is 10 is 1 over 3 ln 2 plus c. Can we solve for c? Yeah, you subtract that thing. c is 10 minus 1 over 3 ln 2. That's what the c is. All right? If you want to know this, that's just a number, right? You can plug it into your calculator if you want to. That's a number, whatever it is. So what's our final answer? Our final answer is this formula here, but with this number instead of the c, because I don't want to see an unknown constant in the answer. My final answer, f of x equals 2 to the 3x over 3 ln 2 plus c, which is that. 10 minus 1 over 3 ln 2. There you go. This is an initial value problem in which you are told the derivative and you're also told some specific value. Using the derivative, you take the antiderivative, you get the function, you use the specific value to find the c. Let's do a couple more. All right, this is actually a very simple problem when you boil it down to the mathematics, but it's very realistic. I looked these numbers up this morning myself. The Falcon 9 rocket, this is the rocket that Elon Musk wants to send people to Mars on. The Falcon 9 rocket engine, it delivers 7,500,000 newtons of force. I don't care if you know, you don't have to know much about what all of this means. Newtons is a measurement of force. Let's say the rocket engine delivers this much force. That's just how powerful the engine is. If you don't know much about newtons, this is very, very powerful. And the mass of the rocket is 500,000 kilograms. Very, very heavy. The question is, if we start at rest, find me a formula for the velocity of the rocket when you blast the engine. All right. What do you have to know? So this is a physics problem, basically. You have to know just a few little things about physics in order to answer these questions. The first thing you need to know is, how does velocity relate to forces? Well, they are related by some sort of intermediate, which is the acceleration. So one thing that we know is if A measures the acceleration, it is a fact that A of t is the derivative of the velocity, right? Another way of saying that is the velocity is the antiderivative of the acceleration. So we could write it this way. Velocity is the integral of A of t dt. All right, so this is how you find the velocity if you know the acceleration. What is the acceleration? The acceleration can be determined by this force and this mass by Newton's law. If you've ever taken a physics class, probably you learned Newton's law, which is F equals ma. This is how the force measured in newtons is related to the mass measured in kilograms and the acceleration measured in meters per second. In this example, we were given the force and also the mass. So in this case, the force was 7,500,000 equal, and then the mass, I told you, was 500,000. A, and you can solve this for the acceleration. A, divide 7,500,000 divided by 500,000 is 15. So in this case, A is going to be 15. So that means the rocket is accelerating at a constant speed of 15 meters per second per second. All right. How do we find the velocity? That was the question that we're given. Find the velocity of t. Well, it's the integral of the acceleration. So that means velocity is the integral of A of t, which is just 15. Now, the A of t could be a function which depends on t, but in this case it's not. It just is a constant. All right. And now we're at the point where I say this is actually very easy once you boil it down to the mathematics. Can you do this integral? Yeah, you can. I hope you remember from last time. What do you get when you have just the integral, the antiderivative of a constant by itself? You get that same constant times x. Now, it's not x in this problem. The variable is called t. So what I get is 15t plus c. As always, we get plus c. So the velocity is 15t plus c. And now we need to solve for the c as before using the other piece of information. Now, if you look back at the problem as I wrote it, you don't really see another piece of information, at least not clearly stated. Although, if you look carefully, you will see I said if we start at rest. So when I said start at rest, this was the initial property or the initial value in disguise. Start at rest means that the velocity at time 0 is 0, right? At time 0, the velocity equals 0. And so this we can use to solve for the c. This means I plug in t equals 0 and then set everything equal to 0. And what it says here is 0 equals 15 times 0 plus c. And can you solve for c here? Yeah. C is 0, right? 15 times 0 is 0. So it just says 0 equals c. All right. So what's my final answer? It's this, but with the value of c, c equals 0. My final answer is velocity of t equals 15t. That's it, plus 0, right? Yeah, it is pretty simple. This is a very realistic problem because actually if you want to measure the speed, how fast a rocket is moving, this is basically the only way to do it, by measuring the force that your engine is producing and then measuring and then doing the antiderivative. The reason this is the only way is because, like, to measure how fast a car is going, you can measure how quickly the wheel is spinning or something like that. But a rocket flying in space, there is no fixed reference by which you can measure how fast it's going, right? The car has a wheel which is turned by the stationary road, okay? But the rocket doesn't have anything that it's running on. There's no way, actually, there is no physical way to measure how fast the rocket is moving directly. You must just keep track of how often you ran the engine. I suppose you could measure based on like the rocket's distance to the Earth or something, but that requires very precision measurements of some kind of distance sensor going to the Earth or the Moon, which are typically going to be very far away. You're better off just measuring the rocket force and doing the antiderivative. All right, here's one more to do. This is more of a biological example, medical, if you will. Let's say that N of T represents the number of cancer cells in some kind of sample. Let's say we're growing a sample in the lab, which we're trying to study the growth of some cancer. N of T is the number of cancer cells available in the sample, and it's increasing over time, of course. And let's say we also know that N prime of T is this. Now, how would you actually know in the lab what the derivative is? Remember, the derivative of, if this is the number of cells, the derivative would represent how fast this number is changing. And so I can imagine a situation where it might be easy to measure, like, how many extra cells do we get every day? Even if you don't know how many the total number is, you can measure how fast it's growing, right? So let's imagine we know how fast it's growing. And here's my initial condition. On day 0, we had 300 cells. And your job is, first of all, give a formula for N of T, the total number, and part B, say how many cancer cells existed on day 10. Let's see if we can do it. So for the part A, I am given the derivative. I want to find the original function N of T, so I take the antiderivative, right? N of T is the integral of N prime of T dt. Let's start again up here. N prime of T I gave you was 60e to the 3t, and I'm doing the integral of that, dt. Okay, you got to remember your rule for e to the power kx. Remember, we had a rule for that. It was 1 over k e to the kx. So this is going to become, 60 stays like it is, 1 over 3 e to the 3t plus c. All right, and just because I'm going to have to do more stuff, I might as well simplify. 60 times a third is 20. So N of T is 20 e to the 3t plus c. All right, we're not done yet. This is a formula for N of T, but I have this extra unknown constant in here. So now we have to solve for c using the initial condition. The initial condition said the number of cells on day 0, which I would write N of 0, is, what did I say? 300. The number of cells on day 0 is 300. And so, in order to solve for c using this information, I plug t equals 0. N of t equals 300, right? So it says 300 equals 20 e to the 3 times 0 plus c, and I want to solve for c. E to the 3 times 0, e to the 0 is 1. This is 20, so this is going to say 300 equals 20 plus c, and solving for c, I get 280. All right, so my final answer for part A is this, but with 280 instead of the c. (20 e to the 3t plus 280). This is the answer for part A. All right. What about part B? Part B said, how many cancer cells are there on day 10? Well, having already figured out this is a formula for N of T, for part B, we want to know what is the number of cells on day 10. That's just N of 10. And we have a formula for N of T. So for part B, all you got to do is plug 10 in for T here. N of 10 is 20 e to the 10 times 3, right? Plus 280. And this is just some number you can put on your calculator if you want. e to the 30 plus 280. Just because this is a word problem, I decided to plug this into my calculator, and I got, this is a very big number. E to the power 30 is huge, but in the scientific notation, it's 2.13 times 10 to the 14. So a very, I mean, you expect this number whenever you ask how many cells are there. Cells are really small. So a very big number for the answer is not unreasonable in this case. That's how we do initial value problems.